Hi everyone. In this video, we're going to continue on with our discussion about sampling distributions. And we're going to start off here with a random sample. And the idea or why we're talking about a random sample is that if you remember in the graphic that I was drawing in the last video, uh, it relied on taking many samples. Uh, and further than just taking many different samples, each of the samples needs to have a certain property or certain type to that. So the paradigm, in a sense, that we were working with when I took a bunch of those samples last time is called the repeated sampling paradigm. And that should make sense because I repeated sampling many times to get that histogram. And so furthermore than just taking many samples is that each of the samples need to be what are called random samples. Okay? And so if we look down here at this definition that I pulled from the book, we have random variables x1 through xn. And in a sense, that's our collection, that's our sample. Okay? And those collection of random variables are said to form a simple random sample if of size n, okay, if each of the random variables are independent of each other and each has the exact same probability distribution. Okay, so that would mean if I'm looking at GPAs and I'm selecting people randomly to ask their GPA on campus, that would mean that the GPA of the first person that I asked should be independent of the second person that I ask, and that is likely true. And then the second part is that each has the same probability distribution. So in theory, so this is a bit theoretical to think about, but in a sense, everyone has the same probability distribution where they're about their GPA. Okay, and that probably is weird to think about that there's a probability distribution associated with your GPA, like with your singular one, about where it could come out, and that second part may not be true for GPAs in a sense, but let's assume it is, that each one comes from sort of the same distribution. Each person has sort of the same abilities at the college, and so it's just as likely that they could have a GPA of, or everyone has the same probability of having a GPA of 4 and everyone has the same probability of having a GPA of 2 or something like that. I know that wasn't the greatest explanation of what it is, but these are the two properties of a simple random sample. In practice, in this class, most often we're going to say yes. No matter what, we're going to say yes, it is a simple random sample, and we're going to move on with our life. Okay? Now, we can combine, in a sense, when we describe this, we can combine 1 and 2, and we can call this, so if things are independent, 1 and they have the same probability distribution, 2, we call them independent and identically distributed. And we shorten that by saying IID. Independent and identically distributed. Okay, so if things are IID, say IID normal with a mean of 0, standard deviation of 3, that means that every single x, every single random variable that I sample has the same probability distribution, normal 0, 3, and each one does not affect the other, meaning they're independent. Okay, so let's move on to something that I think will be a little easier to understand, or will make some more sense, other than not, make some more sense more than random samples. So these sampling distributions are going to be extremely important to our discussions later on in the chapter, and in the rest of the course. And so it's important to get them, or it's rather necessary to continue on with many of the problems that we're going to face. And so we need to get the sampling distribution. So we can derive them or create a sampling distribution of any statistic using two different strategies. So the first strategy is calculations based on the probability rules that we know. Okay, and so mathematical calculations based on those rules, and what we get is an exact sampling distribution, okay, or a theoretical sampling distribution. And that's great. That's sort of an ideal situation. A sort of less than ideal situation would be to carry out a simulation experiment to obtain an approximate sampling distribution. Okay, and so that's in a sense what I described in my big picture that I drew in the last video, was the second one. Okay, the first one will come about by, in a sense, taking an infinite number of samples and creating my picture from an infinite number of them. But of course that's not realistic, and so we have to turn often to the second one. And so sometimes, maybe even more often than not, that first one is either very hard or impossible to do. So sometimes it might be actually impossible to derive a sampling distribution using probability rules. And that's why we need to turn to the sort of more dirtier way of carrying out a simulation experiment, right? And so at this time, what I want you to do, or what I'm going to do here, is show you an example, a sort of interactive example of how you can create a sampling distribution, or how they are created. And so I'm going to exit out of here, and I'm going to go to something called the Rice University Virtual Stat Lab. So Rice has a Rice University is in Houston, Texas, and it's a very good school, and they've created this virtual stat lab, which is a bunch of like web apps that show different statistical ideas, so on and so forth. And so one is a sampling distribution. And so it has some nice pictures here that will go through the idea of how sampling distributions are created, and in fact will return to this idea in later sections of chapter 5 to see the interesting ways that sampling distributions behave. Okay, and so we have a population distribution, okay, which they call the parent population, and we can change how it will look, and we will in a second. Okay, but we have the parent population, and then we take a sample from that population, right? And when you have the sample, then afterwards a statistic is calculated from the data. Right? And so the first thing that we can look at is a mean. Right? And so first we need to figure out what sample size we need. And we'll say, which we do down here, we'll say sample of size 10. So I'm sampling 10 things. And so what happens here is I sample 10 things, and then specifically what this app defaults to is creating a mean. Okay, so I take a sample of size 10 there, and then I find a mean. And the idea is that I do this again and again and again. So if I keep clicking the animated button, it will give me a different sample each time. So if you notice the bars or the dots are falling at different places every time, and that leads to a different mean every time. Okay, and I could keep on doing this again and again and again, and it's going to lead to a distribution, or it's going to lead to where the blue bars are. It's going to lead to an approximate distribution of how the sample mean behaves. And so I can do this, let's say we'll repeat this 100,000 times. Okay, I click 100,000, and then if you look and see here, there's a histogram, in a sense, in the third picture down. That is the sampling distribution of the sample mean when I have a normal parent population. And so we'll come back again and look at this more critically later on in chapter 5. But that's the idea of a sampling distribution. And of course, we can have things that are different from a normal population. So maybe I want a uniform-ish population. Okay, so then when I take a sample here, sorry, let's clear the lower three. So when I take a sample from the population, I do this sort of again and again and again. You'll see, because my parent population is uniformly distributed through the whole sample space here, that my samples vary more than usual. But it turns out when I run 100,000 resamples, okay, I get something that looks like that. Again, this is a distribution of the mean, sample mean, when n is 10, when the sample size is 10 and the parent population is uniform. Okay, and so I can do this with all kinds of parent populations and see how the sample mean behaves. Okay, so that's an interactive discussion there. And another way that I can show this is actually with the programming language R. Okay, programming language R, and we're going to have some, you may, if you want, we'll be able to have some practice with using R that I will show you in class, not on the video, but in class. And so we can do this type of simulation, again, just what we did the last time, okay, in the Rice Virtual Stats Lab, but we can do it ourselves with code. And so in this code, I do a few different things, and so surely it will seem weird to some of you, probably more than others, if you're not familiar with programming languages, software, so on and so forth. But here I'm making in line 9, I make a vector of length 10,000. So I want to make 10,000 means and plot them. So I make a vector of length 10,000 and I make it a double, okay, just so I don't have any sort of problems. So again, this has all kinds of side effects in the sense that you need to know a little bit about the language. But basically, I make a container which is going to hold my means. Okay, and then I make a for loop here, which I think almost everyone in here is sort of familiar with a for loop. Each language does it differently. Okay, basically a for loop is saying for a set amount of iterations, I'm going to perform what's ever inside of it. Okay, and so what happens in here, I want to make a sampling distribution of the sample mean from a normal distribution with mean 0 and standard deviation 5. Okay, so inside I create an object called samp, okay, whatever that is. And what I do on the right side here is I sample 100 points. So in a sense, I'm taking a random sample of size 100, okay, from a normal population with mean 0, standard deviation 5. Okay, so I take in the Rice Virtual Stat Lab, I took a sample of size 10. Here I'm going to do a sample of size 100. Okay, so sample of size 100 from that normal population. Then I take the mean of that sample of size 100 and I store it in my container, in a sense, up here. Okay, so I run this. I run line 9. Okay, then I run lines 11 through 14, which will iterate through and repeat this process 10,000 times. Okay, and then at the end I make a histogram of my means, and this is my approximate sampling distribution. It describes how a sample mean is going to behave from that certain population. Okay, so now back to here. Okay, so that was from the Rice Virtual Stat Lab and R. And so let's go a little bit further into the simulation steps just to make sure we have everything. Okay. For a simulation, to get a sampling distribution, you need the following things. You need what statistic you're interested in. It could be the mean, it could be the proportion, the standard deviation, the median. Any summary of data is a statistic, and so every single one has a sampling distribution associated with it. And so first you need to know what statistic you're interested in. Second, you need to know what distribution that you're sampling from: normal, Weibull, uniform, exponential, gamma, whatever. Okay, there's a bunch that we know. 3, you need to know the sample size. So how many samples are you taking each time you take a sample? And then 4th, you need to know the number of samples to take, or the number of iterations. And so we'll call the sample size n and the iterations k. So here's how you run the simulation. So it's the same thing sort of that I did in R, but here's a sort of different way of thinking about it. You take a random sample of size n from the population distribution. Okay? Then you calculate the statistic from that sample. Great. You did that once there. Now you need to repeat steps 1 and 2 k minus 1 more times. So I want to sample a random sample. Sorry, I want k samples total, or k statistics. And so I need to do it k times. And then at the end, you make a histogram of the k statistics that you calculated, and that histogram is called the approximate sampling distribution. Okay? And so this leads to the your turn. And this is not a usual your turn, okay, because it's not going to be due on Monday, but it's going to actually be due a couple weeks from now. It's your second project. Okay? And so for your second project, you are going to simulate some sampling distributions. And so what I'll do is I'll give you a write-up of different simulation conditions, and you're going to simulate a number of different sampling distributions for me. Okay, so we'll discuss how to do this in R, which is very similar to what I showed you. We'll also discuss how to do this in Minitab if you're sort of scared of R, scared of programming. Um, there is an option for you to do this in Minitab. Okay. And then if you want to do it in another language, maybe like Excel, or if you know Python, if you like Python, you can do it there as well. Okay. And so if you want to do those, I'll be of limited help to you, but I can help. Um, and we'll discuss all the sort of details in class. Okay, and so that's your sort of your turn is to get ready for that discussion in class, and that ends this video.